Greetings, I'm Greg Bailey from GreenArrays. We're engaged in a new project, which is to make fresh training videos on the use of our chips and of our programming tools. This video is intended as a precursor to and to establish context for all of the following tutorials. We'd appreciate it if you would try to accommodate the attitude we would like to see in viewing these things. We would like to introduce the essentials of our way of doing things, and we would like to link you to resources that you may find helpful after you've seen the other videos or even before. We have some experience in adult education. Programming is a craft more than anything else. It's certainly not a science. To acquire the craft of programming, one does much the same things that he does to acquire a martial art, if you will. In training adults in martial arts, whether they be Tai Chi, internal arts, or whether they be shooting or any other damned thing, it is appropriate that the student actually study and perform and practice the way being taught. It is very bad practice to come in and immediately try to accommodate the discipline being taught to one's current methods of doing anything. Why would one be learning something new if one simply wants to hammer it into the patterns of one's old techniques? So we ask that you practice our way while learning and wait until later to decide whether or not you want to diverge from our ways. In that way, you at least know what our way is and know how to do it correctly. The essentials of our way are minimizing complexity of development tools. When I began programming in the mid-60s, a small compiler was typically 4 inches of fan-fold paper worth of source code. The resulting complexity was substantial. Operating systems were typically 6 or 8 feet of stack of fan-fold paper. The first Forth system I saw was 20 pages of source, and it reproduced itself with no external help. So there is a minimization of complexity of development tools, which is the essence of our methods. Secondly, we don't believe in solving irrelevant problems. The first thing one often does is to think, I'm going to do a statistical algorithm here, and so I think I will make a library for all possible statistical problems. Don't. You don't have those problems yet. You don't know what their dimensions are. You don't know why or in what context you would be using them. Don't try to make a tool for a problem you don't find in front of yourself. Deal with what is actually there, and that means you need to understand the actual problem, the problem as stated by the problem itself, not necessarily by someone trying to write a problem statement, and solve that problem as directly and simply as is feasible. What kind of problems am I talking about here? Well, what kind of problems indeed? Quite often when presented with Forth, the first thing a programmer will think of is I'll write a text editor. We are about applications. What are applications? Is text editor an application? Yes, but it's a trivial application. Applications that are interesting are things like calculating asteroid orbits, determining the velocity vector at ballistic missile engine burnout to hit a target on the other side of a planet, assessing driver fatigue, fusing data from intelligence sources to infer the command post locations of an enemy, managing energy use in a building to minimize peak power demand, controlling throttle and dynamometer to precisely produce an engine performance profile, detecting and cataloging internet attacks in real time given millions of attack packets per day or 30 or 60 per second. These are problems, and one of those problems warrants your effort on only those things necessary to solve it. We believe in programmer portability as being very important. You need to be able to sit down in front of any one of our Forth systems on any computer and know how to operate it, know how to write code in it, know how to test code in it, know how to maintain source in it. Consequently, we tend to depend only on those tools we write and provide because we can control them over time. In 1979, I had the privilege of going down to the Forth Inc. offices in Los Angeles and sitting down with Elizabeth Rather, Chuck Moore, Dean Sanderson, and myself We were tired of all forth systems that we were using being different. We were tired of not knowing what we were going to have available for tools on a particular system. We'd been making systems for all kinds of processors, from microcomputers to mainframes. We had been doing this in the context of application programming, and because of human nature, we were, of course, trying new things on every system. The result, unfortunately, was chaotic. I could not sit down and know exactly how I would go about testing and proving that I had solved a problem adequately and bug-free on a given forth system that we'd made. And so we decided to standardize at least the environment a programmer worked in. And that was our concept, programmer portability, not software portability. We defined the polyforth model to absorb all of the things we felt were essential to have in a working forth system to write application code and test it, and to make that model common across all classes of processors. Would it optimally use every processor? No, that's what the application is for. But the system, the tools, and the environment, and how one goes about doing things, we wanted to stabilize. And that's what we think we did. There was a common set of tools with no capricious changes, no wonderful human interface improvements every 6 months just to make the marketing guys have something to talk about. Screw that. Waste of time, bad for programmer morale, and we're programmers, so we want to have our morale intact. Use standard abstractions that adapt to the hardware as necessary. We don't force all machines to be 16 bits wide. It's useful to have and practical to have the arithmetic cell size be the same size as the address range size is. Things vary, cell sizes vary, you accommodate that, but it's annoying to discover that you need to use a double precision number to address memory. That's mind-boggling. That's technique breaking. Addressing units vary, of course. Bytes are the common method of addressing memory these days. Some of the machines are cell addressed. The NCR mainframe, the last NCR mainframe that I programmed was still cell addressed. And so you impose whatever you need to impose to make the environment comfortable. You adapt to the hardware where it's appropriate. You abstract the hardware where it's not appropriate. The programmer interface. We have a single common program interface consisting of a QWERTY keyboard and a 25 by 80 display. Yes, that's old. Well, it's also very practical, and it can be produced anywhere in the solar system over a telnet connection. It certainly works a lot better than remote desktop does to a system on the moon, let alone Mars. And so we use something that works regardless of context, and it's something that we can use to get into working systems on site anywhere that has some communication capability. So we don't see any reason to improve that by making it into a GUI. Common management of mass storage and of source code is also important. By the way, with respect to GUI, one of my customers at Athena Programming was a blind man. He was perfectly capable of doing everything a programmer needed to do without sight. Try that with a GUI. Mass storage. We like to see mass storage organized in directly addressed blocks of 1K octets. That looks very much like the way old-fashioned disks were addressed. It's exactly the way that modern USB devices are addressed. Modern USB devices look just like block-oriented SCSI devices. The sector size is, that's a variable that you tweak as necessary. So a sector is 512 bytes, so we use 2 sectors per block. No big deal. And so, the most modern stuff we have around still can be directly addressed in 1K byte blocks. The big advantage, I don't need no stinking file system to address mass storage if I know the number of where something is on it. Also, nobody can screw up my ability to access that item which is stored at that numeric address. We can, of course, create more abstractions on top of it. File systems are common for application purposes. Is a file system necessary to program? No. We organize our source code in blocks. Each block is a, if you will, paragraph or a page of code. You tend to put code that's closely related in a block. You tend to try and put code in a block that's complete within the context of the block and can be described and documented and the purpose of it explained. We identify blocks by their addresses. We can, of course, again, assign names to these addresses. We can create a directory of these things, but it's not necessary in order to program the computer successfully to have those things. Also, on embedded systems, those things are superfluous, often are very superfluous. I'd much rather have TCP/IP running on my embedded system than a file system on my embedded system in most application cases. We tend to look at our source code as an array of characters. 16 lines of 64 characters is common, and that's how we do it in our method of looking at it. Our text editor and other tools look at it this way. We look at it that way. We print listings with 3 blocks per page. We organize comments, or documentation more accurately, as 1 block of documentation per block of source code, separated by a distance in address space. But we quite often, when we print listings, if we do print them for reference material, put the shadow, if you will, the documentation, adjacent to the source code that it describes. What do we put into the block of documentation? Well, we don't describe what the code does, because, of course, you can see exactly what the code does by reading the code. That's not necessary, it's superfluous. But what is not necessarily obvious is what the hell is the code for? What do you use it for? How do you use it? When do you use it? Are there any side effects to using it? These are the things we discuss in the shadows, the things that are often absent from any form of documentation in many people's code. We encourage making it possible for somebody else to actually absorb your code and do something with it. That's a handy thing to be able to do. Common basic utilities. We only have a few utilities because there are only a few utilities that are necessary. We have a text editor, which is line and character oriented, and it's very hard to screw up your source by falling asleep at the keyboard, as it is with many text editors. You fall asleep and your wrist falls down on the keyboard and you start hitting a key that does something to your code. And it does it repeatedly as long as your hand is still on the keyboard until you wake up and say, wait, what have I just done? And you look and you can't see what you've just done. Now you have to use some diff tool to look at the effect of this on a potentially very large source file. No, we don't have things like that. We don't want things like that. We want you to do something definite, like hitting the enter key at the end of each step of editing a piece of code. And if you don't consciously hit the enter key, nothing is changed. It's a simple editor. It's the same editor on all systems, all environments, works fine on embedded microcontrollers, works fine on mainframes, and it works fine over Telnet. Disking is a simple utility set for copying and moving and comparing large volumes of disk, or small. And that still works on everything. That's how you take a backup to a USB device. A USB device is just mapped into the block address space, and you copy the stuff from here to there, and there happens to be the USB device. You unplug the USB device and take it away. Nothing special needed. Debugging and testing. Forth is outstanding for software testing because the difficulty of testing software is usually the code does too much, and so you can't really assess its boundary conditions. And you have to write a test program and debug it before you test anything. No. Why is code complicated? Why is a subroutine complicated enough that it's hard to test? It's because the overhead of getting into and out of a subroutine in most programming paradigms, such as C, for example, is humongous. Would you make a C procedure whose purpose was to add 2, 3 vectors? Why? Okay. Look at what has to happen in order to invoke a procedure to add a pair of vectors and give you a vector back. In C, which uses a stack, but it misuses the heck out of the stack in our view, you begin by pushing a description of the 2 vectors onto the stack. You either push them literally there or you push pointers to them. But anyway, you have to push them onto a stack. They weren't on the stack to begin with because you can't use the stack for data. You push them onto the stack, and then you push a return address on the stack, and then you dive into the procedure, which begins by immediately ripping those vectors off the stack and putting them into local variables or registers or wherever it's going to put it. So it can then do the vector add, which is a trivial operation, and then push the vector or a description of the vector back onto the stack, return to the return address, and at the call point, now I have to pull those things back off of the stack and put them in my local variables again so I can use them, or into my registers, wherever I'm putting them. Okay, all of that moving of shit off and onto the stack before calling the procedure is what makes it attractive to write big procedures rather than small procedures. So a C programmer wouldn't make a procedure out of a vector add if he was at all interested in efficiency. Whereas for us, it's trivial. The numbers are already on the stack. That's where we manipulate data. Data that are actively being manipulated are on the stack by nature. And so we just call with a simple call instruction, no pushing the things on the stack and popping things off because we don't need to. They're already there. We call this procedure. The return address goes in the return stack, not the data stack, so it's not in the way of the data. We get to the procedure, we do the vector add on the stack, we eliminate one of the two and leave the answer there and go back. The overhead on this is the call instruction and the return instruction. That's the only additional overhead opposed to inline code to do the vector add. So it's very efficient. So we do things like that. And once you have a procedure that does something simple like a vector add, you can test it to exhaustion. The next level of procedures that you make on top of a vector add are also then things that you can test to exhaustion because you don't have to doubt the vector add in the first place. And so it goes. We don't use typically anything more than the fourth interpreter because for simple enough routines, most of which are that simple, you can test them by hand by giving them the boundary condition values and watching whether they get the right results or not. We also can display and change memory. We can do all of these things, but they're all trivial. So the debugging and testing environment in Forth for us is very easy. We don't need tracking programs. We don't need trace programs. We test our code as we write it from the bottom up. Once we've acquired and justified our confidence in the bottom code, we don't have to mess with it anymore. We just use it. It becomes a utility. It becomes part of the language. As is commonly said, Forth is an extensible language because in that sense, every time we build one of these tools, it becomes part of the programming environment. It becomes something you can use as a programmer while you're building database. It becomes something you can use as you're building the program. And it also is something that you can reference easily. The rest of the documentation that one would like to have is posted on the website, typically of GreenArrays. We're not going to discuss in great detail the entitlements of a polyforth system because these are already documented very well. The reference manual, DB005, on the GreenArrays website is the original polyforth reference, which is the common entitlements of using polyforth. Each implementation of polyforth was expected to have a CPU supplement, which documented the adaptations made to the hardware, special features added for one reason or another, anything that was differed from the reference manual. There is such a manual for the GA144 in DB006 on the GreenArrays website. The code in ArrayForth 3 that runs on a Win32 platform is Athena Programming SaneForth system, which is a derivative of polyforth. The manual for the generic x86 aspect of that is in the SFPRM document, which is on the GreenArrays website. And the specifics of the Win32 adaptation itself are in SFW32PR, also available on the GreenArrays website. So it is desirable to get familiar with all of these documents about the polyforth model, especially if you've never used one. We will talk about them as if they're part of basic life and as natural as breathing air. I've been using polyforth, since 1979. So to me, it's extremely natural, and I will tend to speak blithely of these things as though they were as natural as breathing air. If that's not the case for you, read these manuals. It's worth the time. The Array43 User's Manual, DB013, is also on the GreenArrays website. There are a whole lot of manuals on the instruction set, architecture, chip, I/O, etc., and uses of these things on the GreenArrays website. I encourage you strongly, if you're planning on programming the GA144, to go and read these things and study them and learn what you can from them. There's also a book, Starting Forth, written by Leo Brody, which is available at the forth.com website, and which I encourage you to look at just for insight into the thinking that was going on back in the 70s when we were implementing all of this. And you may, of course, look at the various introductory and tutorials which we've made as videos that are on the GreenArrays Inc. channel on YouTube. Some people look at our interface, our programming interface, and regard it as old-fashioned. I am an old-fashioned programmer, I think, by definition. I learned to program before you could take a course in college in programming. And we began maintaining large text files, humongous text files. And we began using, eventually, text editors that you could operate interactively. We didn't have very many interactive computers in the mid-60s, but as time passed, we made tools that looked like text editors and used them on these large text files, and then eventually we were editing the large text files interactively. That is, to me, old-fashioned programming. It was a breath of fresh air when I realized that you didn't need to have the resources of a mainframe or of a giant file system or anything else. You could have next to nothing on a microcontroller and maintain your code. And then I realized how much time I had spent correcting regressions as I maintained code in the old days. You would make an inadvertent change. And it was hard to find inadvertent changes. It still is hard to find inadvertent changes. When you look at a large text file and diff it against another one, something that tries really hard to figure out what you did to it will try and show you the differences. But quite often it will show you those differences in such a way that you really cannot be sure what you're looking at because something got moved. And when it got moved, part of a line of code here looks like it was taken from a line of code down there. It wasn't. They just happened to match, and so it decided that it would show the differences that way. Diff is not a particularly user-friendly tool. That's the kind of thing that we were using way back then in the 60s and early 70s, and guess what? That's still what we're using on GitHub and Virtual Studio. So I don't think that our method of maintaining source code in blocks is old-fashioned or DOS-like. There was no DOS involved. We were writing code before DOS was a thing. So get rid of that mindset. Just like thumbs up versus thumbs down when you're shooting a pistol, right? Some people will say you should always have your thumbs up. And some people will say, no, use your opposing thumbs and get a tighter grip this way. Now, when you go to a shooting class with John Farnham, even if you're an absolute firm believer like I am in thumbs down, opposing thumb grips, you will shoot thumbs up to learn what he's teaching. Do it here. Use our methods. Don't immediately start figuring out how to maintain fourth source code on GitHub. That's not the problem you're looking at. The problem is you're looking at how do I exploit computers the way these guys have been doing for years. How do I exploit the GA144? Concentrate on the problem at hand, which is the new stuff. Don't try and turn it into your old stuff immediately. You will have a richer experience for it. And thank you very much. I wish you well.